Hello, everyone. My name is Colin Brace, and I'm here to give my presentation on control moment gyroscopes. So, what are control moment gyroscopes, or CMGs? So, a control moment gyroscope is a mechanical device that stores energy as momentum to be used for later. Um, Angular momentum is proportional to the moment of inertia of an object that's spinning, and then the angular velocity of the object. You can see our equation down here. Pretty simple, L being our angular momentum tied to I and omega. When it comes to practical design, good CMG design spaces mass farther out from the axis of rotation. So we get that largest angular momentum with the least amount of mass and slowest speed. Getting those high speeds puts stress on the bearings. We don't want to oversize our bearings by too much. So spreading out that mass and lowering the speed is better. And then we get a high moment of inertia. And again, we're just trying to maximize how much angular momentum we'll get. How do they work? CMGs are very, very unintuitive to think about. When I was learning about them, I found this video that was super helpful. So CMGs are mounted with either a one-axis or two-axis gimbal system, which is controlled through a gearbox by a pretty precise computer system. By spinning the rotor mass, by rotating the spinning rotor mass in one of the gimbal axes, it creates a moment in the orthogonal axis to the spinning axis and the axis that you're actually gimbaling it about. So that's called gyroscopic precession. If I'm spinning my rotor around the x-axis and I tilt it in the z, it'll make a moment in the y. Now, a really good video to explain this phenomenon using a satellite analogy, which breaks down the mass into individual satellites and then combines them back together, is this one I found online. And again, it helped me, so I thought it might be helpful to show the class. Just as he said, if we're applying a force in that in an axis against that spinning, it's going to apply in the orthogonal axis. And if you think about our rotor, our mass, it's just a bunch of satellites all spinning around that central axis. Let's talk about applications for a second. So what are they used for? Control moment gyroscopes are run by electric motors that are powered by solar panels. Um, in space, it's a huge application because they use electricity rather than fuel, which again makes them ideal, but for large scale operations, and they're non-refuel. They're in applications that you can't refuel. Thinking about a space station or something bigger like that, you can't co-up all the time and give it more thrusters or more fuel to run their propulsion thrusters. You just really need them to be able to maneuver when they can. And that's what the electricity is helpful for. CGMs work in groups of two, and they spin in opposite directions, working in tandem to maneuver the spacecraft. And then larger arrays obviously are needed for heavier spacecraft. They spin in opposite because as they're spinning up, there's a kind of residual yaw as that spinning creates its own torque. And so if you have one spinning in the opposite direction, when they tilt together, they'll cancel each other out in that spinning, but the other, the precession and the force that's generated will combine. So relevant spacecraft that use it: International Space Station, China's space station, and then the Hubble telescope also uses it too. There's a picture from Honeywell. Okay, limitations. CGM systems in space require a large amount of mass. And so you need to get that all into space. So only these large spacecrafts will warrant these systems that are so heavily to maneuver. Also, gyroscopes have saturation limits. As they tilt off axis, that precession, they go farther and farther and farther away from their base datum point, and they lose their ability to apply torque, as how far they're off axis determines how much energy and moment they're putting into the system. If they rotate completely off, they're going to be applying torque in not a direction you want. And you can desaturate them by applying an external torque, even using like transferring all the momentum in there into like a reaction wheel, which is kind of like a fixed axis wheel. There's no gimbaling there. And then you can just lower their speed and reorient. You can also use gravity, the force of gravity, to desaturate your CGMs, but that's more of a complex maneuver. And then unique applications. These aren't just space. The main success they have is in space, but look at a yacht application. So this company, Seakeeper, they offer control moment gyroscope that will react to the input of waves, and then it will counter the rocking of the boat. So there's a quick video that kind of shows how this guy works. You can also see here that the flywheel is rolling the boat left to right, but it's gimbaling front to back. And that's again showing how, as it's spinning, it's applying a moment in the opposite direction than it is gimbaling around. Cool. There's also self-balancing robots. If you've ever seen MIT's Atlas, they have a CGM in there and it keeps it stable. And again, what makes it so stable is just like a car. Like let's say you have a school bus moving at 5 miles per hour. It's going to be really hard to stop. If you have a toy bus, you only get 5 miles per hour. It's going to be very easy to stop. When you have a lot of mass spinning up at a high angular velocity, any rotation, the mass is going to resist that, just like that huge school bus is going to resist you stopping it because of the high mass. So that'll keep it stable and it will not want to move off axis. A couple more applications for us is here is a startup called Lit Motors. They have a concept car that is developing self-balancing. So it uses two opposite spinning CGMs to control the roll of the car slash motorcycle. And so I can get rid of this pop-up. There it goes. You can see the two control moment gyroscopes right in the car as it breaks out. And you can see how they'll tilt forward and backward, just like in the yacht example, and it will control the roll of the car rather than anything else. It's getting pulled from the side. You think it would fall over, but the CGMs are counteracting that. So it always stays up on two wheels. Pretty neat application. And just like the Seakeeper application, and unlike in space, these gyroscopes are evacuated. So they're in a vacuum. Don't really need to worry about that in space, but that lowers friction and it lowers wear as there's nothing else going on in there. It's just the parts and it's in a vacuum. I hope you enjoyed. Thank you.